Hi everybody, my name is Caleb Billadou, and today we're going to be covering Lab 2. So the purpose of this lab is to create a computational model of two charged tapes that exert electric forces on each other, and then use this model to estimate the amount of charge on each tape necessary to float one piece of tape above the other. And we're going to compare that to the previous lab, Lab 1. So the model is the same as Lab 1, right? You just have one piece of tape floating above the other tape. You peel one piece of tape off the other one, and then peel a similarly charged piece of tape, and then you put them next to each other, and then you measure the distance that the piece of tape goes up because they have similar charges. So here's some of the principles we're using from Lab 1, same stuff, right? It's just coulombs, electric force, um electric fields, um, proportional to the distance, same stuff. Now, the one thing that we're using that's different is linear charge density, where you have a total charge divided by a distance that gives you a charge density lambda. So here's a preview of the result, right? Here's the model, and then there's a couple of the values. Cool, so there's the code. As you can see, you have the model on the left where you have two lines of charges. Both are negatively charged, and the bottom tape exerts a force on the top tape upwards, and gravity exerts a downwards force on the top tape as well. And you can see that the magnitude of the electric force is actually greater than the gravitational force, so that's why it would go upwards. And the total charge this time is actually greater than the total charge from Lab 1. On the right, you have some of the code, which just kind of shows the first one, how you would measure the E field. For the second one, you show the E field over a set of radii for a bunch of different points, right? So you can see in the model on the left, you have a bunch of different individual charges, and the second block of code shows the E fields on each individual charge rather than just one charge to another, as in Lab 1. And then the last one just shows the overall calculation, you see the two big arrows on the left, it's the calculation of those big arrows, and then the overall charge from this lab. Now, some of these assumptions, it's pretty similar to the last one, right? We're assuming that the charge is evenly distributed, that the two forces are only electric force and the gravitational force. There's no air resistance. And then the possible errors, right? Measurement could have been bad, right? Like it's kind of hard to measure when the reaction happens so quickly. So discussion questions, what if you had modeled each of your tapes as a single point charge, like in previous lab, compare the estimated values, right? So in lab 1, we got 1.21 times 10 to the negative 8 coulombs. In this lab, we got 3.7916 times 10 to the negative 8 coulombs, and that's about a 3 times increase. Now, it's why do these estimates differ? Which value is most likely to be closer to the real value? The two-charge model only considers one radii, but the charge line model considers all radii, right? So rather than just two charges going together, you had a bunch of charges acting on each other, just giving you a more realistic value. And that's it for this lab.